Hi everybody, I'm Niranjana and today I'm going to be presenting the work we have done on the tool TensorFlow Data Mutator or TFDM. Using this tool, we study ML model resilience in the presence of different data faults. We all might be familiar with machine learning or ML. To recap, ML algorithms learn behaviors based on sample data, known as training data, in order to make predictions or decisions without being explicitly programmed. In recent years, machine learning is advancing all kinds of technology, and it's being increasingly deployed in safety-critical domains such as autonomous driving, the aviation industry, surgery, and medicine. And so ML reliability plays an important role. Faults can occur anywhere in the ML pipeline, which looks like this. So at the data level, the hardware or the software levels, and wherever faults might occur, we need to understand the reliability thresholds of the system under test. Our focus in this work is on the data layer. We develop a tool to assess the dependability of ML applications with respect to different types of data faults. So what are data faults? Faults occurring in the input data that is fed to the ML algorithm are called data faults. Data faults can occur from intentional sources such as adversarial attacks or unintentional sources such as common corruptions to the images, label errors, dataset imbalance, and so on. Let's see an example for each. In the figure on the left, we see that because of an adversarial attack, the dogs in A are misclassified as a person, a cow, and a train in B, even though the changes introduced to the image are not visible to the human eye. And on the right, 4 images in the popular CFAR 100 dataset, which were mislabeled, are brought out in this study. So what's the worst that can happen when there are data faults? Well, when a model is trained with data faults, the model could learn incorrectly and consequently predict wrongly. For example, these images show MRI scans of the human brain. In this study, titled Deep Learning with Noisy Labels, researchers found mistakes in the labeling of certain images. This is because experienced human annotators missed some lesions in the figures. These are in red here, and so they were labeled incorrectly. So in a safety-critical medical application, which then learns from this dataset to predict whether there is a tumor looking at MRI scans, learning from these incorrect labels can lead to bad consequences where the tumor is not identified. Let's look at what other researchers have done to address this problem. So a lot of work has been done to mitigate the effects of these faults. So in the case of noisy labels, tools have been developed to identify the mislabeled instances, add denoising layers, and employ deregularization techniques. In the case of imbalance in datasets, resampling, clustering, and ensemble learning techniques are used. There has also been work to first evaluate the test data and improve the test data. So deep mutation uses mutation testing to create different mutant models and evaluate the test data that is fed into these models. A deep test generates new test data using different transformations. So in the presence of new test data, the model has increased neuron coverage, making the model more robust to data faults. But there has not been any work which evaluates the ML model resilience itself to different data faults, and this is the focus in our work. So to address this need, we developed an open source tool called TensorFlow Data Mutator, or TFDM. And we use this tool to study any ML model vulnerability to data faults. And our fault model includes both unintentional and intentional data faults. We support a total of 6 different types of data faults for different ML applications. We evaluate with 7 popular ML benchmarks with respect to these different data faults. Our tool can be used for both faults in the training and test data, but we consider mutations applied during the training phase, as most of the faults we model occur in the training data. Here we list the types of faults with their source and modeling in our tool. First, missing and repeated data can occur because of dataset imbalance resulting from the nature of data collection or different database errors. We model these as data removal and data repetition faults. Next, if there are implementation errors in the model, or if the model under consideration is sensitive to the order of training data, the model accuracy changes when the training data is shuffled. So we model them in data shuffle faults. Next, we model noise perturbation faults. Although the different sources of noise is unlimited, we model 4 representative noise types that can be added to the input data. Finally, we model the consequences of human labeling faults such as random label errors and the consequences of adversarial attacks as both random and directed label errors. This is also referred to as untargeted and targeted misclassifications. And here we have the different consequences of these faults. We now move to the evaluation of our tool. We use the standard metric called silent data corruption, or an SDC, to interpret our results. SDC here means a mismatch from the expected output of a fault-free run. So in ML models that perform an image classification task, an SDC is the incorrect prediction of the image label. Here's an example showing the effect of SDCs in the CFAR10 dataset, where a bird is misclassified as a ship and a dog as a horse because of data falls. Finally, the reason we use SDC and not accuracy as the metric in fault injection studies is because we want to strictly evaluate the model resilience to the faults alone, so we only consider data points that were predicted correctly without faults. Whereas accuracy cannot capture this as it considers overall model performance, which means it includes the cases where the model predicts incorrectly because of reasons other than the particular fault under consideration. So we use YAML files to specify the fault configuration. Once that is specified, we inject the data faults before training and then train the model with the faults. We choose 10 random inputs to observe the SDC after each fault injection run. We calculate the error bars at the 95% confidence interval. And we see that the errors range from 0.01% to 3.09%. We evaluate on 7 well-known ML benchmarks and 3 open source datasets. So these are the different fault configurations. Including all of them, a total comes around to 500,000 fees and around 10,000 compute hours. So we ask research questions which relate to each of the fault types under consideration. While we explore all the different faults in the different archives in our paper, we focus on 3 here in the presentation in the interest of time. These are different amounts of training data removed, training data repetition, and random and partly directed labeling errors. We will see what each of them is and the evaluation. Now we visually show what each fault type does, followed by the evaluation with that fault type. So to use data removal faults, we specify the percent or amount of training data images to be removed from the dataset, and this is randomly chosen each time this operation is called. So let's say this is the total dataset. These are images from the CFAR10 dataset. So when the total dataset contains 10 images, 10% removed would be 1 image removed, 50% is 5, and 90% is 9. Of course, when we apply the tool to the actual CFAR10 dataset, which has 50,000 training images, the tool automatically removes 10% or 5,000 images in it, or the amount we specify. After removal, the model is then trained with the reduced dataset and tested for SDCs. Now let us look at the results of applying this fault to the different ML models and datasets. These are the results from the first experiment. On the x-axis, we vary the amounts of training data removed from 10 to 90% in increments of 10%, and on the y-axis, we observe the SDC rates for test data after training with the reduced dataset. We find that most models are highly resilient to data removal, and only when the model is more complex or the dataset is more complex, more training data is required to be able to predict correctly. For example, AlexNet, which is the most complex CNN of the lot, requires more training data than the rest, and RNN, which is the second most complex model next to RNN, it closely follows AlexNet. Regarding dataset complexity, we find that MNIST models perform poorly only when 90% of the data is removed. Similarly, CNN with the CFAR10 dataset is less resilient than the CNN with the MNIST dataset. Next, let's look at what data repetition faults mean. Here we repeat the specified percent of the dataset, and again, the exact images to be repeated are chosen randomly each time the operation is called. Let's consider the same dataset as before. 10% repetition means one of the images, here the red truck, is repeated. 50% means 5 images get repeated. These faults are pretty common when data is collected from multiple sources. In the musical GT-Zan dataset, for example, researchers found that there were at least 50 exact repetitions of musical excerpts and many more other kinds of repetitions. Let us now look at the evaluation. Performing a similar experiment with different amounts of training data being repeated from 10 to 50%, we find that the results are very similar to data removal faults when resiliency decreases with increasing model and dataset complexity. This is expected because repeating or removing 10% of the dataset is equivalent to training only with 90% unique data points. Let us look at what random label errors mean. So in the label error fault type, we mislabel a specified percent of training data. In random label error, we choose the data to be mislabeled randomly. Looking at the same dataset, we can now see the labels for each of the images below too. So when 10% is chosen to be mislabeled, one of the images is mislabeled. For example, the cow is mislabeled as a cat here. When 50% is chosen, 5 images are mislabeled as shown. These errors are untargeted and model human errors in the dataset, like in the examples of the brain images that we saw before. We have now understood what random label errors mean. There are 3 types of directed label errors we support in TFDM. The first 2 are partly directed label errors, also referred as single-sided targeted misclassifications. So here, either the label class to be mislabeled or the label class to be mislabeled to are chosen according to some user-specified condition, and the corresponding classes to be mislabeled to or to be mislabeled are chosen randomly. The third type is double-sided targeted misclassifications, where both the classes to be mislabeled and the classes to be mislabeled to are chosen based on user-specified conditions. Directed label errors model adversarial attacks where the class-based misclassifications can be targeted. So in this experiment, the x-axis shows the different percentages of training data that is randomly mislabeled. The left shows random mislabeling and the right shows the partly directed mislabeling. The y-axis shows the STC rates for the different models when different percentages of training data is randomly mislabeled. So we see a more uniform drop in STC rates for the different models for random mislabeling. And this is expected because when the feature maps are randomly weighted, the model cannot learn to attach a label to the feature meaningfully, and so the predictions uniformly deteriorate with higher rates of mislabeling. But when mislabeling is directed to the immediate next class label, we find that the models are less resilient with the drop in STC rates starting before at 50% compared to 70% in random, and with less difference between the STC rates across the models. So to summarize the different results for the different research questions, in the first one we saw that the more complex the model or the dataset, more training data was required. And for second, we saw that the results were similar, the first one, and MS models, they perform well with just 10% of unique data. And for the third one, we saw that there is a gradual drop in STC rates for random mislabeling, whereas there is a more sharp drop for partly directed labeling errors. We list 3 potential directions in which our tool can be extended. So using a TFDM, we can explore and evaluate the differences in dataset resiliency. For example, for a same dataset, we can use different models and see how the dataset alone performs with different data faults. We can then also use the tool to understand the correlation between resilience and model test accuracy. We can integrate TFDM into bigger projects. For example, our group is currently working on characterizing the diversity of models with metrics other than accuracy. We borrow the metrics from economic theory such as Gini coefficient and Shannon equability theorem. We can apply n-version programming and majority voting with the tool to tolerate data faults. So our work is step 1 of a 3-step process where we first evaluate the model's resilience to different data faults. Step 2 would be identifying, and step 3 would be mitigating. And finally, we can improve the tool to include more different types of faults. For example, common corruptions and concept drift, these can be modeled with adding and removing different classes in the dataset. And larger datasets can be supported with more GPU resources. So we can use distributed training for larger datasets. Currently, we use patch training. And we can also make the tool more generic to any ML framework by using NumPy operators. So in summary, we present different background of the faults and the attacks at the data level in ML applications. We discuss the modeling of various fault modes to corresponding data mutators in the tool. We provide understanding of error resilience of ML applications under data faults. So we found that different models have varying resilience to the same kind of fault. We found that resilience to data faults decreases with increasing model and dataset complexity. We also found that certain classes of the dataset are more vulnerable to faults. Our tool is open sourced and available at this URL, and you can contact this email for any further clarifications and queries. Thank you.